And so now let's get back to resonance and finish it today. So what? Just to refresh, we were looking at oscillating system with natural frequency omega naught. Then, of course, we expose it to some medium, right? So as a result, there was a damping force, right? And as a result, there was a damping. And then we added a driving force, right? So now the system is driven. And we decided to look at the force which varies harmonically in time, right? And so we ended up with inhomogeneous second-order differential equation, and solution of which consists of two parts. General solution of homogeneous equation plus any particular solution, right? So a general solution of homogeneous equation we knew, right? And it gave us a transient solution, right? And since there is a damping in our system, so if you wait long enough, that transient solution will disappear sooner or later if you wait longer than a decay time, right? Decay time is 1/beta. And the second part of the solution is a particular one, right? And we solved it, right? We found the particular solution, and of course it was particular solution was, and we called it a steady state solution, right? So x, it's a response of the system, right, equals amplitude and cosine of omega t minus delta, right, where omega is the driving frequency of the driving force. So basically, our system response, right, oscillates with the frequency, with the driving frequency, right, with the driving frequency. So as I said, if you wait long enough, transient solution disappears, only the steady state solution lives. So we decided, okay, so we're going to emphasize only on this solution, right? And so A, probably I will write A, the value of A, right? So this A squared, I guess I should be able to squeeze it here. A squared was the amplitude of the force, but you remember it's not a force at this moment, F. It's an amplitude of the acceleration, because this F small, how did we get F small? We took F capital, which is the force, divided by the mass. So that's how we introduced this F. So this is basically amplitude of an acceleration, right? Units of acceleration has units of acceleration. And divided by omega, okay, let me grab my notes, omega naught squared minus omega squared to the power of 2 plus 4 beta squared omega squared. So that was the amplitude. The delta, I will write it maybe in 15, 20 minutes, right? Because only then we will start discussing it. Right, and so this is the function of omega, right? So it makes sense to search for a value of omega where A is the maximum. Again, how are we looking now at the system? So we assume that the system is given, so natural frequency is given. The system is exposed to a certain medium, so beta is also given in fixed constant. This is also constant, so everything is constant except for omega. So we're sitting and tune our driving frequency of a driving force. All right, let's assume it's tunable, and we basically tune it from 0 to infinity in a search for something, right? So we search for a maximum point, or the frequency at which response of the system, amplitude of the system is maximum, and we solved that problem. We found that A is maximum when omega, we call it omega 2, equals to omega naught squared minus 2 beta squared, and we call it a resonance frequency. Right. Okay, just quick refreshing everything. So that was our resonant frequency, and the maybe I will write also square of maximum amplitude, right? So basically, if you plug omega 2, we ended up with f naught squared divided by 4 beta squared omega naught squared minus beta squared, right? And of course, if we assume a light damping, and pretty much at this point we ended up, so for light damping, when beta is much smaller than omega naught, then we ended up with a max equals, of course, approximately equals to f naught divided by 2 beta omega naught. And now, of course, if damping is very, very light, right, beta is small, okay, assuming that these are fixed, right, then of course amplitude of the system can be too big, and of course it can damage the system, can ruin the system, can destroy the system, right, because any system has some limitations on amplitude, right. Okay, so that's where we ended up, and I wrote there, yeah, it's possible to damage a system. Now, so we found resonance, and now let's just plot it. Let's plot a few things, right? So let's plot this amplitude. And we're still going to plot a squared. Okay, let me frame it because that's the one of the most important things for now. Right. So let's plot a squared. I will put a small bullet. So let's plot a squared. I will probably do it here. Yeah. So it will be a to the power of 2. And then, again, we treat the system as everything is given, fixed except for omega. Basically, we tune our driving frequency to see the or measure response of the system, a squared. So when omega equals 0, we're going to have this is 0, f naught squared divided by omega naught squared, some constant. So over here, we're going to have, which way I label it, just a naught squared. Yeah, and the value you can easily see. And of course, this curve is going to reach maximum at this frequency omega 2. Right. So let me show that this is somewhere. Oh, you know what? Let me move it slightly more to the left. So this is omega 2, and let me draw a dash line. And the curve will have this bell shape. Oh, maybe even steeper. Okay, good enough. So now we have several frequencies. Now let me show all these frequencies on this curve. So first of all, resonant frequency, right, omega 2. I can show that this is, of course, corresponds to the frequency omega 2 equals square root of omega naught squared minus 2 beta squared. It's a, you know what I will use here, sort of extend and write on that side also. So this is resonant frequency. Then frequency of the system with damping, omega 1. Let me show it here. So this will be approximately omega 1. And of course, omega 1 is larger than omega 2 because you remember the expression for omega 1. It's a omega naught squared minus beta squared. Resonant frequency minus 2 beta squared, frequency with damping, frequency of the system with damping, it's minus just beta squared. So I call it frequency with damping. So this will be our frequency with damping. Right. And then the last frequency which described the system, natural frequency. Basically, the frequency of the system when there is no damping. So this is omega naught, right? So omega naught, of course, there is no expression Of course, you can write it square root of k over m or k over I, depends on if you have a point mass or rigid body. Okay, I will just write it's a natural frequency. Natural frequency, right, when there is no damping. And of course, omega in this case is driving frequency, and in this case, it is a variable, right? And of course, all these frequencies are at the same spot only when beta equals to 0. Beta equals 0, the natural frequency and the resonant frequencies are the same. Now, another plot. So let's look at the system when it's exposed to different medium, different beta. And again, the same. So first, let's say the system is in a vacuum, and we tune the frequency from 0, driving frequency from 0 to infinity to see response of the system, right? To see the amplitudes of the system. Then maybe we can expose to air. It will be small beta again. Tune the system. Tune the frequency, change the frequency to see the response of the system. Then maybe water, then oil, right? So let's just plot for different beta. So this curve and for different betas. I will probably plot it underneath over here, right? Now, I will put a new bullet. So let's change betas, right? Okay, so let me estimate the space. I think I should be okay if I plot it like this. So again, this is a squared. This is still our driving frequency, right? And now, response of the system. First, no damping. Beta equals to 0. Of course, if beta equals to 0, all these frequencies are at the same, equals to each other. All right, so let me show that omega naught about this point. Let me see. Right. So this is omega naught, natural frequency. Right. And if beta equals 0, then of course the amplitude will be basically maximum, right? Maximum, and so let me draw a dash line first. I said maximum. Amplitude will be infinite, basically. Amplitude will be infinite. Why did I say maximum? All right, and so let me plot it. So maybe I use red for this curve. So first, this point goes to infinity. So we're going to see something like this. And it will come from infinity on this side of the natural frequency, resonant frequency. So that's the case when beta equals to 0. Right. Of course, the system is basically destroyed. Now let's add damping. And so what will happen? So now, of course, all these frequencies are different. So maximum will be shifted. So natural frequency, of course, stays here still, right? We cannot change natural frequency unless you change the system, K and M, right? So, but we're not changing the system. We're changing only environment, the media, right? So if we increase beta, now it's not 0. So of course, omega 2 will be shifted, and natural frequency, not the natural, resonant frequency will be at the lower frequency. Maybe over here somewhere, right? So let's say this will be omega 2, right? Which is of course smaller, and of course now amplitude will be finite. Amplitude will be finite. Maybe it will be here somewhere. Right. And if we plot it now, it will be something like this. Oh, it should be maximum over there. So it's getting narrow. I mean, it's getting, amplitude is getting smaller, and it's getting wider. It's getting wider. Then Okay, let me show that this is beta is larger than 0. So this is beta 1 larger than 0. Then if we increase beta even more, of course, then the curve, the resonant will go even to lower, maybe somewhere here, right? And the curve will look like this. Oops. So again, it's getting, amplitude is getting smaller, maximum amplitude, and the curve is getting wider. Right? So this will be for beta 2, which is larger than beta 1, and so on, right? You can continue. So you see it's getting smaller and wider. Probably I will write it here. Okay, so if beta gets bigger, the resonant peak gets smaller and wider. The resonant peak gets smaller and wider. Okay, and now, so the key point now, in order to make a transition to the next point, right? So wider. Let's define, or let's introduce the tool which can be used to measure the width of the curve. Let me check if I mentioned everything about this. Right. Yeah. Maybe just I want to also emphasize. So this is basically a squared maximum, right? Which we calculated, right? Okay, so now how can we measure the width? Okay, small bullet, and how to describe the width? How to describe the width of the curve? I will just replot this, and I need to erase these frequencies, information about these frequencies. Probably I'll do this way. So this omega, and now it's still a squared. And let me just replot this. It will be something like this. Okay, it goes to 0 over there, right? But here it's a finite value. Right? Okay, so how can we, for example, measure the width of this curve? Let's say this is, you know what? Let me here write a max. Okay, it's a max, and here a squared. Because a max I needed that point. So how do we measure? So a max squared. Take half of that. Find half of that. Right. It will be somewhere over here. So let's say a squared maximum over 2. Draw the horizontal line. And this frequency distance between these 2 points is called a full width at half maximum. Half maximum and full width. Right. Okay, full width relative to the center, because you can also use half width, full maximum, but right. So this is f full width at half maximum, FWHM. It's a very, very common term if you're going to work in optics or laser physics, right? Full width at half maximum, it's almost everywhere, right? When I worked at STL, right, on my PhD, it's like everyday tool, right? So full width at half maximum. So let me write full width at half maximum. Full width at half maximum. So it's okay, like in my notes, it's interval between the 2 points where a squared is equal to half its maximum height. Then, yeah, an abbreviation. So FWHM, very common term. And what if we have a light damping? Because in lots of systems, like laser system and so on, it's a case of light damping. So for a light damping, so let me write for a light damping. Again, light damping, it's when beta is much smaller than omega naught. Regular weak damping, just smaller than omega naught, but in an extreme case, when this is true, then, of course, for light damping, so the resonant frequency is almost natural frequency, right? So this will be basically natural frequency, and it can be shown. So in this case, it will be basically omega naught. It can be shown, and there's a problem. I used to solve that problem, and then a couple of years ago, I stopped solving that problem. It can be shown that in this case, the full width at half maximum equals to, of course, in case of light damping, equals to 2 times beta. In case of light damping, full width at half maximum equals to 2 beta. So basically, it means that, yeah, in case of light damping, this is basically a resonant frequency. This point is, okay, let me show it like this. So it will be omega naught minus beta. And of course, the other point will be at omega naught plus beta in order to have width of 2 betas. So this will be omega naught plus beta. Right? So the width, in this case, 2 beta, full width at half maximum. Again, as I said, used in optics a lot. Right. Then, there is another parameter which shows how sharp the resonance, this peak, resonant peak is. Right. And that parameter is called the quality factor. Right. So let me introduce it, and then I will tell you when I first time heard about this. And so this is first bullet. Now the second bullet. Again, all these parameters which can be used to describe this resonant curve. So the quality factor, the quality factor, Q, capital Q, is used to denote it. Yeah, it shows how sharp the resonant is. So it shows how sharp the resonance. Right. Okay, probably I should underline the quality factor. Okay, so it is defined in this way. Q, actually there are 2 expressions, but of course let's start with the first one, and then of course we will compare them. It will be equal. The resonance frequency Of course, in this case, yeah, it's a natural frequency, but because it's a case of a light damping, resonant frequency basically equals to the natural frequency. So that's why omega naught. Because again, in most of the systems where it is used, we have very light damping. So divided by the width, full width at half maximum, divided by 2 beta. So it is a one way of defining this quality factor. Right? And of course, the good system, oscillating system, right, must have a large Q. For example, like a good clock must have large Q, I don't know, Q of 1,000, right? Because in that case, the system is much more selective, right? So if this is large, so the curve is very narrow, sharp. And in this case, for example, let's say radio station, I mean the radio receiver, right? So if you have a sharp resonant peak, and then let's say there are some noises or maybe some neighboring radio station kind of nearby, and if your curve is sharp, then of course that station, right, that driving force of that station is not going to produce significant amplitude in your system, right? So in order to produce significant amplitude, that neighboring station, frequency of the neighboring station must be very, very close to the frequency of your station, right? But if your Q is small, then this curve is very wide, and then if that station, that neighboring station over there, so in that case, of course, it will produce some reasonable amount of amplitude in your system, response of the amplitude, response of the system. And of course, you will hear something, some two stations at the same time. But of course, if it's a sharp, then the amplitude will be very small, produced by neighboring station, and you will hear just, and it will be on the level of noise. So it will be on the level of noise. And then the same with clock. A good clock must have a quality factor very large. In that case, resonance is very sharp, right? So any disturbances, any from the environment is not going to change the frequency of the system, change the work, and as a result, the clock can go faster or slower, right? Right. But of course, a bad clock, of course, will have a wide quality, a small Q and wide resonant peak. Then, what else? Yeah, let me first give you a second expression which can be used to find the quality factor, and then I'll tell you when I first heard about this and started using that. So the second, so let me put it's a, I know, kind of one, and now the second way of calculating the quality factor. So let's just massage this expression, formula, not formula, omega naught over 2 beta. And let me rewrite it in this way. Let me move beta upstairs, 1 over beta. Then, yeah, it's omega naught. Then, let me introduce also pi, 2 pi, and omega naught. I will take it even lower. And now, in order to make it correct, I need to multiply it by pi. Okay, these manipulations. And so now, what is 1 over beta? Again, it's a weak damping. Beta in general, of course, it's a damping constant, right? You remember 3 classes ago we introduced. But in case of a weak damping, it's also a decay parameter, right? Decay parameter which describes how fast the system dies out. Right? Sorry. And then, of course, 1 over beta is units of time, and it's called a decay time. So if you wait over that period of time, 1 over beta, amplitude of the system gets reduced by a factor of E, 2.7, right? So that's decay time. And so this is a decay time. Then, okay, let me write that first. So pi, and upstairs we have decay time. And then what do we have downstairs? 2 pi over frequency. It's just a period of oscillations. Period. Right. So that's the second way of looking at this quality factor. So what's the meaning of this? Okay, let me plot this system. Right. So let's say this is amplitude. This is a max. But now I want to plot it not over omega, but over time. Something like this, right? So let's say this is time, and it will behave something like this, right? So I probably should have made it longer. T, right? Okay, so first I want to see decay time, 1 over beta. Again, as I said, it's a moment of time when amplitude gets reduced by a factor of E. So this is a maximum. Let's say at this point, it's T equals 1 over beta decay time. The amplitude is, let me use some different colors. So here, so this is a max divided by E. All right. So this is, the whole thing is decay time. Right. Then period, what is period? Period, we can see this distance, okay, time. Period, this is period, the same period stays the same, right? As system oscillates. So this is the same, okay, of course not in my picture, right? But it's supposed to be the same. It's supposed to be the same, right? So now if we take the total, if we take the decay time and divide it by the period, what are we getting? We're getting basically number of cycles that system managed to make before its amplitude gets reduced to this point, to this value, right? So if system is kind of decaying too fast, right, dies out too fast, right? So of course it will be able to make only maybe a couple of cycles, right? And in this case, Q will be small, kind of not a good example of a system, oscillating system. But if Q is large, in this case, system can make a much larger number of oscillations, right, cycles before it reaches that point. So in this case, Q is larger, right? So basically, this is, I can write interpretation, of course, this is a number of period or cycles in one decay time. So it's a number of cycles in one decay time. Right. Okay, so now, when, probably I should frame this as well, right? So when do we use this and when should we use this? What's the major difference between this definition of the quality factor and that definition of the quality factor? It depends what you do in your research. If you're sitting, for example, right, I don't know, like, yeah, in optical lab, right, and surrounded by, you know, you do work on a spectrometer or spectrum analyzer, right? So all your work is around frequencies, right? So in that case, if you want to analyze your oscillating system, right, the resonance of your oscillating system, then of course you will use this, because all your information right now is in time domain. So this formula is useful if you work in a time domain. But if your system is doing something and you're measuring whatever of your system, response of the system on a spectrum analyzer, or not spectrum analyzer, oscilloscope. Basically what you see what system does in time. So if you work in a time domain, then of course this formula is much more convenient to work with, to use, right? So this is for frequency domain, this is for time domain. If you read the paper, you will read, for example, like noise analysis of a system, right? So I've done at some point plenty of that, right? So of course, every time they either analyze it in time domain and then frequency domain. And of course, there are some transitions, right, in order to get more information, right? So for frequency domain, and that is useful in the time domain. Okay, so let me write it. Useful in a frequency domain. And this is, of course, useful. Where should I write? Okay, I will just write underneath of this. So useful in a time domain. So let me check if I mention, yeah. So now, I remember first time I heard about this quality factor when I started working for Dr. Waldman. He is the founder of STL, the richest lab at the university, right? And he was explaining me about the lasers, right? And he used the word quality factor first time. So let me just tell you where it is, why do we need it in a laser? For example, some semiconductor laser. Let me see if I can erase this. Let me see. I think after this I will go to phase. Yeah, so I should be able to erase this. So it's basically application of quality factor. So Q in a laser. So you know how laser works. So you have some active medium, right? So material, sapphire activated with titanium or something else, right? And of course, so it's active medium. Active medium. And so basically it's a material which produces light. Right? And this active medium produces light if you measure the spectrum, right? So some intensity of your light versus frequency, basically in the frequency domain, right? So it will give you what is called the gain curve. Gain curve, it will be very wide curve. So this active medium will usually produces light in a wide frequency range, right? It's called gain curve. Right. Okay, so that's what active medium produces. But of course, in order to produce laser, you need to sort of put the active medium between two semi-transparent mirrors. And those very often just these edges, right? So these sides of the active medium very often work as a semi-transparent mirrors, right? So, right, semi-transparent mirrors, right? And basically, these mirrors, they form what is called a Fabry-Perot cavity. Fabry-Perot cavity. So light basically oscillates between these two mirrors, getting larger and larger amplitude, right? And then, of course, it's a semi-transparent, so of course, light is also getting out, right? So from this side and from that side. Okay, so that's, and so now, this Fabry-Perot cavity, let me write also. So semi-transparent mirrors, it's a FP cavity, basically. It's called Fabry-Perot cavity. Right. And so this Fabry-Perot cavity, it has a resonant frequency, right? it doesn't, it allows to have standing waves only at a certain frequency. Basically, it allows only a certain frequencies, light at a certain frequencies to exist between these, right? So there are basically resonances of a Fabry-Perot cavity. They basically starts basically from 0 all the way to infinity, and they spread equally, right? Sort of equidistant. So they will give us peaks like this, right? So these are resonant frequencies of Fabry-Perot cavity, and they're equidistant, right? So as a result, so gain, active medium produces this gain curve, but of course the Fabry-Perot cavity allows only light at these frequencies to exist. As a result, at the end of at the output of the laser, you're getting only a discrete set of several frequencies. You will get a little bit of light at this frequency, right? Then significant amount of light at this, and then this, a little bit of here, and maybe this. So basically, we're getting laser working in a multi-mode regime. These are longitudinal modes of the laser. And so now, where is the quality factor? Quality factor of this FP cavity. I remember he was telling me, okay, so if you design proper FP cavity, right, so with high Q, large Q, so to get large Q, and then as a result, these resonant peaks will be very narrow, and as a result, your laser is going to have a small line width. And most of the applications, we struggle to get a laser with a small line width. In order to get that, you can do frequency locking or phase locking in order to get basically narrow line widths, because, yeah, lots of applications, especially in astronomy, for example, right, requires that. So high Q of FP cavity in order to get narrow line widths of the laser, right? So let me show that. Here, high Q is needed, right, so that these resonances, right, to get a laser with a narrow line width. Right. So if you have a narrow line width, then you don't need some create additional parts of the system to stabilize the frequency, as I said, frequency stabilization or phase locking, right? In this case, you can use laser directly without additional parts, right? So high Q is needed, right? Then what else I want to mention? Yeah. So probably, I don't know, 1/3 of my PhD was about getting narrow line widths, stabilizing the frequency, phase locking the system, right? Quantum cascade lasers, right? It was fun. Especially working with Dr. Waldman. He's retired now. Right. I miss those days. Right. So now next, let's look at the phase. So when we found that solution, particular solution, you remember we had A amplitude, and then we also had cosine omega t minus delta, right? So, and that delta, we haven't discussed anything. So now let's look at that phase delta. So what, probably I can erase this. It was sort of kind of digression. It's the first time when I get so deep into this. Right. Actually, this stuff was discussed there was a course, again, my advisor used to teach lasers and applications, but once he retired, so that course basically, it's still being offered, but it's not run. Okay, so now the phase of resonance. Now let's look at the phase of resonance. Phase of resonance. Okay, so the expression, okay, let me rewrite from my notes because I don't remember at the top of my head. So delta equals, of course, arctangent of 2 beta omega divided by omega naught squared minus omega squared. So that's what we have. And let me just plot it, right? Of course, I'm not going to analyze this function. You can easily do it by yourself, right? So I will just draw a plot. And again, for different betas. Again, we're the same assumptions. The system is given, omega naught is given, right? So, and we expose system to a different medium, right? Changing beta. And for each beta, we tune the frequency of the driving force. As a result, so let's plot. So let's say this is delta phase. Then this is driving frequency, omega, and omega naught, natural frequency. Again, let's just talk about light damping, right? So in this case, if let's start with the case when there is no damping, beta equals 0. If beta equals 0, again, you can plot it, right? Or you can use the software. You will get something like this. So first, before natural frequency, resonant frequency, in this case, they will be the same. The phase difference is 0. After the resonance, okay, let me also show here that this point is pi over 2, and this is pi again. And let me draw asymptote, right, and also this. So at the resonant frequency, there is a sharp transition, and phase changes by pi. Okay, let me show that this is when beta equals 0, no damping. So what does it mean in terms of behavior of the system? So it means that when driving frequency is below the natural frequency of the system or resonant frequency of the system, right? Then system, because system responds instantaneously. So it doesn't lag behind. So the force is the maximum, the response of the system is at the maximum. So the pendulum is at the maximum displacement, right? So then if force is the minimum, then the system is at the minimum. So the system responds instantaneously. Then, but if you increase the frequency, driving frequency above the natural frequency of the system, then the system lags behind by pi, basically out of phase. The system is out of phase. It just, because it still has inertia, so it's not capable of responding to the fast changes in the of the frequency of the driving force, right? So over here, system will be out of phase completely, right? So the driving force is at that maximum, and the system is still at the other side. Then, what if we add small amount of damping? So beta is larger than 0. So in this case, we will have something like this first. This. So basically, it goes through pi over 2 at omega naught. So this is beta 1, let's say, larger than 0. Then if you increase beta even more, of course, it will be something like this, but still goes through pi over 2. At the resonance, it's pi over 2. So now this is beta 2 larger than beta. And of course, as you keep increasing, this will become less and less steep, right? But every time at the resonance, the phase difference is pi over 2. How come? And actually, I remember when I was a postdoc at STL, right, a couple of years, we tried to stabilize the frequency of the gas laser. So we tried to create a feedback loop, right, and move I erased it, one of the mirrors of the lasers to stabilize the frequency. And we had to take in account if where the noise is most of the noise and where is the natural frequency, right? So because if the noise larger and we need to compensate for that noise, then of course the system would respond with an additional phase difference pi, right? And then we will have to add that additional phase difference to in a feedback loop, right? Of course, I'm not describing the details, but I'm just telling you that it's not just for mechanical, in the class mechanics, right? So stabilizing the frequency of the laser, and we had to use these results. We had to recall all this information. So yeah, back to pi over 2. Why phase difference between the driving force and the response of the system, x, is pi over 2 all the time at the resonance. So let me write the question this. Why delta equals to pi over 2 at the resonance, And I usually give this semi-conceptual explanation, justification. Again, so kind of from philosophical point of view, what do we create at the resonance in the system? Again, so let me just again remind you, I already mentioned this a couple of classes ago. So we have a system, and if it is exposed to a driving force, basically it is exposed to energy in the outside world. So through the driving force, we send energy or provide energy, send energy from the outside world into the system. And of course, because there is a damping, that energy also leaks back through the outside world. So we have this kind of channel of energy, right? And what happens at the resonance? At the resonance, we have the maximum possible response of the system. You cannot do any better than what you can get at the resonance, right? So you have limitations. God created nature this way. So basically, at the resonance, you have the maximum response of the system. It means that you create the most efficient way of delivering energy from the outside world into the system, right? And of course, you can say the most efficient way of delivering energy per unit time, power, right? Dumping power from the outside world into the system, right? So let's recall then if it's the maximum amount of power is delivered, then let's recall the expression for the instantaneous power, of course, instantaneous power, right? It's a force times the velocity, right? Okay, let me write this down. Okay, let me first explain and then I will write down. So force times velocity. So in order to get maximum power, so force must be maximum, and velocity must be maximum, right? So when do we have maximum velocity? Let me first draw it. Let me draw a couple of plot response of the system and the driving force, right? And then I will write in words explanations. All right, so if I plot F versus T, and here below X, again, X is a response, right? A displacement of the system from the equilibrium, X versus T. Okay, so if I plot this amplitude, I think we use cosine function, yeah, cosine. Something like this, right? So here, the maximum force. All right, so at this point, we have F max, right? And so again, the power, it's a force times velocity, right? So at the resonance, force must be maximum, and at the same moment, velocity must be maximum. So when does the system have maximum velocity? When it passes the equilibrium point, right? So now if I plot it, okay, let me overlap it first with this curve. And so at that moment, the system must go through the equilibrium, right? Then reaching maximum over here, then going to, okay, distorted, right? Something like this. Right. So what are we getting? We're getting cosine function describing the force and sine function describing the response of the system. So what's the phase difference between them? Pi over 2. So every time, in order to get maximum amount of power delivered into the system, there must be phase difference between F and X, pi over 2. Right. Okay, let me write that down now. Okay, so at the resonance, again, it's not a proof. It's more like a justification, right? And now, if I ask you, okay, I will write that down words. Let's say you have a child, right, and you want to entertain the child on a swing, right? So, what is the most efficient way of pushing the child? Standing at the near the point where the child is at the maximum displacement from the equilibrium, it's not the most efficient way. The most efficient way, if you are standing near the equilibrium where the child passes, right, the minimum point, and at that moment when the child is over here, right, at the equilibrium, you push it as hard as possible, right? So maximum velocity, you apply maximum force, you are driving force, right? So you deliver the largest amount of energy per unit time if you drive the system, right, child on a swing, in the most efficient way, in this way. Okay, and now let me finally write this down. So at the resonance, we create the most efficient effective way of delivering energy or power, energy per unit time, power, right, to the system. Right. So F, not F, P, power P equals, of course, FV instantaneous, right? So, of course, P max will be when you have maximum force and maximum velocity. So, maximum velocity at when the system passes the equilibrium point, and of course, maximum force when it's maximum. So, those two moments must be at the same moment, right? And that happens when phase difference is pi over 2, right? And here, delta, so it's a cosine function. This is sine function, so delta equals to pi over 2. So all the time, if the system is at the resonance, the phase difference is pi over 2. Again, as I said, it's not a proof. It's more like a justification. I'm thinking about the proof, but so far, I didn't get there. Of course, you can prove it just analyzing the curve. It's not a big deal, right? But again, most of the time, very often, I want to also justify it using just simple words. Now, so a few examples, like I just prepared a few pictures, right, and videos. First, at the resonance, skyscrapers, they are tall, right? And of course, exposed to the wind. Of course, they can reach, or maybe even just earthquakes, right? So they can be exposed to significant amount of driving forces, right? So, and of course, if conditions are right, that system can be easily destroyed. Wake up, I'm having here the second laptop. I mean the second computer. Where is it? Okay, the thing is, of course, you can say why I'm not attaching this to the stream. The thing is, when I use, okay, I ran the system through the OBS, right? It's open broadcasting system, right? And it's power hungry. Plus, when I open also at the same time Microsoft Teams, the CPU is very, very close to, very often even over 90%. So I'm just afraid that if I start streaming, right, it will defreeze the whole system. So that's why I'm using TV, right? Display, right? So this skyscraper, right? So they use some kind of tuned mass dampers, they call them like this, right? So this is the top of the Taipei building in Taipei, right? And at the top, there is a massive, okay, right now it's difficult to see. I will show you the sort of model, right? So there is a massive, I don't know, concrete or steel ball, right? Which is hanging on two ropes, right? It's hanging, so it can oscillate. But at the same time, there are a few springs attached to this ball and also attached to the building. So if the building tries to move this way, of course, all those strings will try to resist. Okay, let me show you the the cartoon showing this. You see? Again, I cannot increase, but whenever I go there directly, actually, the simulation becomes much smaller, right? So this is the building, and you see the ball hanging on these two ropes, and there are a few springs attached. So if the building tries to move to one side, of course, those springs on that side will get stretched, and of course, they expose additional force on the building, damping, adding additional damping on the system, right, to the system. As a result, the system can avoid reaching large amplitude, right? So we can avoid getting into the resonance, right, and destroy the system. Right? So basically, most of the actually before I started teaching this, I didn't know about these tuned mass dampers, right? So that's what is used in skyscrapers, right? And this is the okay. Of course, there is a video, but it's kind of you can watch it by yourself. Just easily type right Taipei. It's that skyscraper tuned mass damper. So it's just a photograph of that massive ball, and these are the cords on which it's hanging. Then this video, but Tacoma Narrow Bridge. You've heard about that story probably, right? I forgot, when was it when it happened? I think it's in 40s or in 50s. Okay, long ago, even maybe even earlier than that. Okay, anyway, so it was, I think, in Washington State or in Oregon, right? So there are large canyons, so they built a Tacoma Narrow Bridge over one of these canyons, right? And they didn't take into account that it can get into the resonance. I cannot imagine, right? It's the 20th century. All this stuff was well known. And still they didn't take care of those oscillations, right? So basically, because there are strong winds over there, right? So the bridge went into the resonance. So of course it's slightly different resonance, right? Bridge started oscillating like crazy, right? Of course I can turn it on, but it's a little bit darker. So the bridge was just oscillating, concrete bridge was just oscillating like a piece of rubber. Damn it, about the cars, right? And it's basically in a couple of months after it was opened, it collapsed. But again, I cannot imagine, right? It's 20th century. Everyone knew about the resonances and how come that they didn't put any dampers. It's bizarre. It's just beyond my understanding, really, right? Then, if you, for example, go to the San Francisco, right, Golden Gate, right? When I was there at the conference, it's one of the first places I went, right? And if you go down, there's a small park, and you can see under the bridge there are kind of dampers, basically like a wafers, layer of rubber, layer of steel, rubber, steel, and also they put one of those dampers on a pedestal, right? So to dump all possible oscillations. And of course, collapse was impressive. Okay, over. The story is over. Of course, it was rebuilt, right? But tons of money were dumped into that river. It's again, it's not the one person who designs; it's the whole, I know, companies. Unless they wanted to dump money into the river. Okay. I reduce on purpose brightness on this screen because the previous pictures were almost impossible to see. But as a result, the video was a little bit darker. But again, you can easily Google it by yourself and watch it, right? And plus, you can easily imagine it. And you saw something. All right. Also, in the ocean liners, right, of course, there are gigantic engines, right? Of course, also in order to reduce the vibrations on the ship, right? Of course, there are some dampers used, right, to isolate the engines from the ship itself. Okay, cool. All right, we're almost over. All right, this chapter. So the last piece. Example, I want to look at the problem because in your homework I give you similar problem similar to.
You're muted, I think.
Yeah, sometimes it happens because when I drink water I mute myself so that you wouldn't listen noises, right? Those sounds, and sometimes I forgot. So we have pendulum, just regular pendulum. And it's in elevator. And the elevator, let's say, accelerates up with acceleration a. So let's find the frequency of this pendulum now under these conditions without using some effective whatever. No, everything must come from the first principle, from the Newton's second law. Right. Okay, I will probably do it here. And in your homework, I give something similar, but it's also exposed to, I think, some damping medium. It's just you will have more forces to include, but idea is very similar. Okay, so a pendulum in an elevator. Right. So acceleration is given, L is given, right? Mass, yeah, we can add mass. M, L, A is given, all right? So these are given. So let me draw the elevator first. Okay, let me make it bigger. It should be enough. So this is a rope, and the whole system accelerates up with acceleration a, right? And the pendulum. Okay, let me displace it like this. So this is a bob, right? So vertical line. L is given, M, right? So we need to discuss this, describe it. And of course, we're going to use, yeah, of course, Newton's second law. And of course, we're going to use polar coordinates, which is the most convenient, right? And in order to use that, of course, we're going to introduce this angle, which we label it theta. Okay, theta. And of course, we're going to use inertial coordinate system because I'm planning to use Newton's second law. Although I'm going to position my origin over here, but it's still inertial. Basically, next moment, the system will just run away from this origin. So this is, okay, let me make it slightly shorter. So theta direction. This is, of course, r direction, r hat. Okay, theta hat. And so, of course, we're going to use Newton's second law. We need to show all forces. Right? Of course, forces we all know. So mg, tension, T, right? Then acceleration. I want to also show over here acceleration because now acceleration, this acceleration, plays an important role. So let me use blue for an acceleration here. So this is this acceleration A. And that's it. So these are forces. And now let's recall acceleration over any system in polar coordinates. We derived it, second class, right? So let me write it. So polar coordinates. So acceleration A in polar coordinates AP, right? So that's, let me rewrite. So it's a r double dot minus r theta dot squared. So that's in the r direction set of accelerations. And then plus accelerations in the theta direction. R theta double dot minus Coriolis acceleration, right? So theta dot. In our case, L is, okay, R equals L, it's a constant. Okay, let me write it this way. So R equals L equals constant. Of course, acceleration will be simplified. Of course, it will be minus L theta dot squared in R hat direction and plus L theta double dot in the theta hat direction. Okay, and now Newton's second law. All right, so M MA equals T plus, yeah, MA equals T plus mg in the vector form, right? And now let's write it in a component form, which way I wrote one theta. Let's start with theta direction. So basically, let's project everything on a theta direction. So first, mass times acceleration. Acceleration in the theta direction because of the motion of the system is ml theta dot. So it will be ml theta double dot. All right. Then, but at the same time, we know there is a motion of the whole system up. So there is an additional acceleration. So we need to add it to the acceleration side. So it's a mass times theta component of this acceleration. So this is angle theta. Of course, this is angle theta as well. So component of this acceleration in the theta direction, it will be a times sine theta, right? And positive, yeah. Plus ma sine theta. Okay, so that's the acceleration side. We have two accelerations. And now we need to decompose all these forces. T doesn't contribute anything because it's perpendicular, but mg, of course, contributes, and its a component will be in the negative theta direction, right? Will be minus mg. Okay, I can quickly show. So this will be the component, of course. So this is component. So again, this is angle theta, this is angle theta, so it will be mg sine theta minus mg sine theta. So that's the equation for theta equation. Now let's do the same for r. All right. R, so from this it will be minus ml theta dot squared, yeah, minus ml theta dot squared. Then contribution from the acceleration of the whole system, right, of the elevator. So it will be r direction, it will be negative, right, r, positive r direction this way, so it will be minus ma times cosine theta, minus ma times cosine theta, right? Yeah. And so now forces in r direction, so mg times cosine theta positive, mg cosine theta positive, and tension fully negative, minus t. Right, so system of two equations. Of course, now we're going to assume small oscillations, small angle approximation. Theta is small after this. So of course, we can simplify it all. So this will be, let me use blue. Right, so this will be theta. Right, I just don't want to rewrite one more time. Right, so this will be theta. This will be also in this approximation theta. Theta dot squared. If theta is small, then we assume that theta dot is small, theta double dot is small. So squared term will be too small. Theta dot squared will be too small. So we can drop it. Too small, drop it. Cosine, of course, will be just 1. Cosine, again, will be just 1. That's it. So now let's rewrite. So from the second equation, immediately we're getting, okay, let me just rewrite it first. All right, so it will be ml theta double dot plus ma theta equals minus mg theta, first equation, all right? And this goes minus ma equals to mg minus t. So the system gets reduced to this. So now, basically, it's almost decoupled, right? So t will be equal, so we can find t. So it will be equals, t goes to that side, yeah, positive, so good. All right, so we'll get t equals ma plus g, right? So that's just the tension. And of course, from the first equation, we can get the frequency, right? So mass distraction, right? And we are getting so that theta dot minus a plus g divided by L minus, okay, equals to minus a plus g divided by L and theta. Simple harmonic motion. So the frequency, of course, naturally, we're getting a plus g over L, and of course we're going to get oscillations because of that minus. If we had here plus, we would get sine hyperbolic, cosine hyperbolic functions if you solve this equation. But in this case, cosine and sine. So omega equals to square root of a plus g over L. Right. So that's how this problem should be addressed. Right. So I just wanted to add this problem because most of the time we don't do much with acceleration side. Every time we just mess with forces, right? But I just wanted to show how we should handle the situations like this. Okay, sorry for holding you 7 extra minutes because I just wanted to finish this chapter. Okay, so now chapter 5 is over, and so next class, it's next week, we will start talking about calculus of variations, right? So basically as a preparation for the Lagrangian formulas. Okay, so now it will be completely new stuff. Okay, guys, so if you have questions, right, go ahead. Otherwise, we can call it a day.